you can help me along here. So, okay, we've begun. So I'll just present the share screen. So I suppose we can just share a window. This maybe. Okay, so the main thing. If you go back to our paper, support vector machine model of the universe. Now, okay, obviously your suggestion to use support vector machines to find the decision boundary between the transformed galaxies and the untransformed galaxies was really interesting. But I wonder, can I click this off or will it? Yeah, let's see. Okay, so, and the result of that was that we, well, I suppose I started thinking that maybe some of the galaxies are actually on the surface of the sphere, which is a reasonable assumption to make. But recently I've been questioning my my sort of logic on that and wondering, okay, so the decision boundary is a cool thing to know about, yeah? But maybe it's not, maybe the conclusions that I came to initially are slightly incorrect. Like, how do we know that the surface of the hypersphere is like a circle like this? Maybe so let's say this is the central sphere of the hypersphere projected here. And then we have the outer sphere projected somewhere out here. But then there's also like the kind of interstitial spheres, I feel like if we were to imagine this as a hypercube, then this would be a square, and then we'd have the larger square out here, which is the outer square. But then there'd be how many, you know, like 6 other or 4 other visible squares anyway here. So maybe the surface of the hypersphere is out here and covers like all of these galaxies in here. So that's what I was thinking that we should, especially since we're going to be presenting this information at this conference in, when is it, July?
Yeah, July 9th, 11th.
Okay, so
9th to 11th.
Nice. Okay, so we have some time to sort this out, but I want to make sure that when we go to present, that what we're presenting is, you know, correct.
Good stuff.
So my thinking here is to go back in time and to look at maybe a lot of the work that we did with projection. Hang on, I'll just switch this off. So the resources that we're going to be using here. Oh God, connection failed. Reconnect. Nope. Is that connection failed at all? Good. This doesn't look very stable for some reason. Let's see. Let's go back. Service error. Service unavailable. Close that and start again. Okay, so while that's booting up, we'll search for this other stuff. Now, what we need to do, I mean, another thing that it needs to be, another issue that needs to be addressed, I guess, is it's not in this paper; it's in a different paper. Dimensions, yes, could be in that paper. I think it is. Another issue is this problem of inscribing a hypersphere inside a hypercube inside the hypersphere. Now, what I think I was doing, see, this is something that I need to figure out as well. Okay, so we said that the radius distance based on the decision boundary was 43.2 megaparsecs. And then using like basic geometry and projection and all of that, I figure that if this is 43.2 megaparsecs, the inner cube had to be 21.6 megaparsecs. So the radius of the hypersphere should be 14.4 megaparsecs. So that was my guess. But if we think of the hypersphere as sitting on the tangent plane, then this hypercube has to be inscribed inside of it. It cannot be that the sphere is inscribed within the cube, because then the cube is sitting on it's sitting on the tangent space, which is obviously not what we want. We want these points to be sitting on the hypersphere and then projected onto the tangent space. So there's a very simple equation that'll solve that problem. And so if the radius, let's say we're using a unit sphere and the radius of our unit sphere is 1, obviously, then the diameter 2 and divided by square root of 3 equals 1.154705383. So that is going to be that value then is going to be the value of the points on our hypercube. So the vertices will have those values. So that's very important. So what I need to do now is get the values of the hypercube. I'm going to just paste that number there. Get the values of the hypercube. Hopefully we can get it from a previous notebook I have here. Any of them, or any hypercube projection, that could work. Maybe not. No, maybe a different one. I'll just close that. So we're kind of going back to the 24 cell work. Anything, one of these maybe, no, 24 cell. Okay, let's go in here. This is the work we looked up the last time. If I go down to the end. Nearly there. Keep going. Oh, there it is. Okay. And here's all the information we need. This object ID, the right ascension, declination, z redshift, and then we have the polar transforms, I think. So this should be good to go. I'm going to skip all of that. Skip that. Skip this. I think we want this. Must have missed something. We did. So it's going to take a while to do that, and we're not even sure if that's what we want. So our aim here is to just print out all of the galaxies. So maybe we don't We don't need to do that. We could possibly go back to our original notebook on SVMs. Maybe might be able to use that code and just run it again. So this one. Okay. I should probably duplicate this. Go back here. And we'll duplicate it and then see how we get on. Okay, we'll run that. Close this. Okay, so we have all our, these are all of the coordinates for the 24 cell really. So we need to pick out the ones that are for the hypersphere and also the 6 cell, which is like a 4-dimensional tesseract. No, a 4-dimensional tetrahedron. That's what I meant to say. Now, fermions are part of the other system. They're like the dual of the other group, which is like SL2C or whatever. So my guess is that these are for they're the 6 cell. We do not want 6 at the start. 6, and then so these ones should be the 8 cell, which is the tesseract, right? Oh god. Cell 8. And okay, so if that's true. Yeah, and they're all. See how they're all plus or minus 1s. That's good because then they're going to be on this. You know, they're centered at the 0 coordinate, which is good. Which is where our it's exactly where our hypersphere is going to be centered. So we want to multiply everything in cell 8 by this value because we want it to sit, all of the vertices have to sit on the surface of the hypersphere. So we'll change this to np.array. Close that. Close that. Close that. Now, presumably, these will also want to be on the surface. Yeah, so we'll change all of these to 1. We'll also multiply these. np.array. And we'll just have a print. So I see how we get on with that. We can do it now. Okay, that looks right. So the next thing we want to do is I think the next thing that we need to do is to plot all of the galaxies. But I want a bit of a nicer plot than that so we can really see what's going on. So we might steal it from our previous work if we can. That's going to be a three-dimensional one. Oh, there's all the galaxies in the universe. So that's it turned inside out. Oh no, that is it. That's the right way. Okay, so we don't want a three-dimensional representation at this stage because we're just starting off. We just want 2D version.
This is a galaxy, all the galaxies from James Webb, or where you get this data from?
Yeah, all this data is from the Sloan Digital Sky Survey.
Oh.
I think there's 2 telescopes involved in that sky survey. One is in the US, like North America, and the other one is in South America. I don't know the exact.
Call it close to Canada.
I don't think so, because the name of the place had a very kind of Spanish sounding name, which would lead me to believe it's closer to like California and areas where the Spanish were active. But I could be wrong. I don't know. It was actually quite difficult to find information on where the satellites, they're just giant digital cameras really, where they were located. And so I think maybe the Spanish sounding name was the one in South America. It was like Los something. And so maybe I never found out the name of the US one. Okay.
The US thing is also called, a lot of it's called Los, like Los Angeles,
Los Alamos. Yeah.
Los Alamos. Yes.
Yeah, which just means the in Spanish, doesn't it?
Huh? D probably, right? Yeah.
D. Okay.
I'm not sure. I never checked that.
Maybe this. Yeah, I think it is.
I think Los is very similar to the French Lee, right? Lee, the Lee car,
yes.
Lee car. Very similar, I think. It's a Spanish equivalent.
Right, and it would be because it's the city of angels, Los Angeles, so it's plural. Yeah. That's probably why it's Los. I assume, because you have that in French as well, that it's a gendered language. So, le, whatever, is male. And la, I think, is female. Yeah.
Louvre, like Louvre.
I'm not sure.
The car, they say le car or something.
Is car a French word? No, that's not right.
There was a show, something like that, but they may have mixed up both the English and French, but I don't know what it is.
Le Patisserie. That's the bakery, I think, right? Or like a place where you go get food.
In Paris?
No, it's just in general, like a bakery.
Oh.
Le Patisserie.
Patisserie.
Le Monde, which is the world, which is obviously feminine.
Very close to Latin. It's probably very close to Latin also, right?
It would be one of the Romance languages, a lot similar to Spanish. Obviously, Italian is probably the closest you could get to Latin. Also, I think Romanian, although don't quote me on that, but there's definitely a lot of seeming Latin influence in Romanian.
Yeah. Yeah, 2 main things streams are Latin and Greek. So.
Well, what is this?
Now, the main streams of the languages, the Western culture is Latin and Greek, right?
Yeah, I think so. Well, yeah. And then, of course, Yeah, like because you have the Cyrillic alphabet, which I think is based more on Greek, and then the Latin alphabet. So all the Romance languages have the kind of more Latin-based alphabet. So I think, is it correct that the Cyrillic alphabet from you know, kind of informs more like Russian and those kind of languages? So they're is that what you
I
mean
know
by
English.
the two roots? Yeah.
English,
Again, English
has both Latin and Greek. That's why the extra spelling, you don't pronounce this whole thing, right? Like a lot of the silent words, silent letters.
Yeah, true. But English has a lot of Anglo-Saxon kind of Germanic influence in it, but the interesting thing, yeah,
even Anglo-Saxon has roots in Greek and Latin, right?
That's a good question. Yeah, I guess so. Yeah, maybe it's all going back there. I mean, the interesting thing about English is that it has so many more different sounds in it than basically any other language, really. Like
for Celtic, you are Irish, Celtic.
Right, even more, like far more than Irish even would have probably. And the thing is I suppose because it borrowed them all, like it borrowed sounds from French and from Italian and all these different languages and put them all together, which is why yeah, when it kind of it did that, it's why like people would have a hard time, like from different cultures have a hard time pronouncing all the words in English. You know, even French people. So like when you meet a French person, they have like a very strong accent. And I was learning that the reason why that is because they deal with like a specific group of sounds and it sort of informs the way they talk. But then for like English speakers, they don't have that. So it changes. I guess the way they speak becomes a bit more bland because there's nothing like that really defines the language. Its identity is more eclectic, if you will, because it has like so many sounds in it. It doesn't sound like anything. So
yeah, I was teaching lower grades recently, and we are going through silent words, silent letters. Like no, I said, do you say no? No, you say no. So K is silent. You know, these are like lower grades only. So like that. So I was lightly thinking, oh, maybe it's because of the Greek and Latin that you added the extra letters in there, but you don't pronounce all the. Because in my language, the way you write all the things is the way you pronounce. We have a lot of alphabets. Almost we are more than double the alphabet of English. So all the words, the way you write is the way you say. You know, almost.
Yeah. Cool. Yeah, well, I think like you know the way like you'd have laugh. Well, that's Laughgh. But there's a lot of words like thought, which has like a GH in there that's not pronounced.
Silent. GH is silent.
And I think that GH comes from again Anglo-Saxon kind of Germanic languages. And I don't know where they picked it up. You see, they would have the Germans would and that region would have had their own languages at the same time that the Greeks were speaking their languages, and same with the Romans, obviously in Latin. So they would have all had
Vikings.
So I mean, obviously they're all related, you know, because all the languages, many of the languages are related. So, but you know, they're probably different enough that we couldn't really say that they're the same. Okay, so we're running into a bit of a problem here in terms of bandwidth. I don't seem to be able to get SciServer really working. So that's
you cannot run the program. You cannot execute the program.
It's very slow. It's over a server somewhere in the United States, probably. And
really? You have connection to supercomputers? Do you have any accounts for any connection to
Um,
supercomputers?
no, I'm for sure that that Xi server here is not running a supercomputer, but I think through a different program I have, or a different what would you call it, server group related to that also uses notebooks related to it's called CoCalc, and using that you can I think you could probably do it with Google as well as other places. You can run your code on different different computing software. So I don't know,
Is
like
there is it Unix or Linux or something like that?
No, it would be like you could run it on like Amazon servers or different. I've forgotten all the different names. I could look them up, but I mean, in college, there's a lot of people who, or there's the means to run things on clusters. So they have big cluster computers, and that's too many.
Is it a cluster computer like networking? It connects to different networks.
It does. Does the cluster? Well, it's a network of computers, probably very fast computers that
servers,
when taken together, constitute like what you might call a supercomputer. So they can deal with
like time sharing. I mean, they will do automatic.
Yeah, there'll be time sharing on that for sure. We're gonna have to open this again. And then, so what is the next thing that we have to do here? All of this needs to be converted. I guess these are on the hypersphere already. So they just need to be, and they're 4-dimensional. So they just need to be projected down onto the tangent plane when we get around to that. Okay, so we need this query here because we're getting like 1 million galaxies in the other one, and that's a bit too many. Ideally, I don't really want to change this code though, so. I just paste that there, and then I'll take all of this. All this stuff takes time, doesn't it?
Oh yeah. The computer is supposed to save you time, but the program itself takes time. That's why I stopped, At some point I used to do that. I was quite excited. I stopped doing that and do it paper and pencil. Sometimes I'm much faster than even supercomputers. That's the new things,
I know, I hear you, but I guess because we're dealing with like a million galaxies, and and all of this stuff, that there's just no way that you could do this with paper and pencil, right?
Yeah, no way. Yeah, if you are data crunching, there's no way. It's analytical, you can do it. That's about it. If it involves data, you don't have a choice. You have to use computers.
Well, I think I've probably done the wrong thing here. Okay. Yeah. I told you I was a bit like sluggish today after the week was incredibly stressful.
Oh. You got your PhD thing going on, right?
Yeah, well, the PhD's the actual work is
and your presentation. You are going to Lisbon, Spain.
Yeah.
No, Portugal.
That's right.
Rather. Portugal,
yeah.
Is that Lisbon? Is that called?
Lisbon, yeah.
Lisbon.
Yeah, because Lisburn is a place in Northern Ireland.
Ah, it's very close.
It's just down the road.
So you are going Lisbon in end of May or something, right? Or June?
Mid
In June, May,
June, yeah.
mid June.
So thinking, I mean, that's quite stressful. I do have to do some work on that, but that's like a bit away. So I'll need to obviously just focus on all of that when the time comes. Oh, I think this is completely the wrong notebook. This is a real pain. We might only we'll go on for another half an hour here and see how much we can get done, and then you know,
continue next week.
Yeah, exactly. We can pick up where we left off next week, and we'll probably have more success.
Yeah, and the 11th, the week after, I will do the third episode.
Great. Okay.
We will discuss that. I will get the presentation.
What did I call that?
The interesting thing is that, now I think about it, because why I did history is that we keep going back. So now our history is such a that it's like a dredger machine. I call it like a global machine, like Maxwell used, Damon machine. So I use something. The dredger machine will take us. The history will keep moving automatically to the present day. That's the idea of in documentary. That will be one of the big things. Documentary movie.
I don't follow. so this is like a an analogy. You're saying. Yeah. How does it work?
It works. It's like a globalization of Maxwell, the Damon machine.
Oh, okay. And is it sort of
Maxwell used to use that? Yeah.
It's an idea you've come up with to explain.
Yeah, like time machine. Yeah.
Okay. Well, I don't know. I mean, if you're doing is this part of the history of physics thing?
Yeah, and the time loop is very much important, because time loop is the one that's guiding me. Yeah, eventually, history of physics is very different from time loop. History of physics is essentially what happened at that time, what the scientist doesn't talk about any fictional things, any any other speculation. Just says the way it is, what the fact was. That's it. Exactly. That's all. It's so facto.
Yeah, and then exactly, and then of course when you have your time, research, which is
much later. Yeah, a later episode probably will continue.
That's look forward to that. Oh, look at that. What the heck is going on there? Oh, wait a second. We deleted too many things probably. Size 1. Yeah. Size 1. CLF. Do not want that. Yes, we probably don't want any of that. See what we got. Okay. Lim, this we need. Getting there, slowly but surely.
Oh, good.
Yeah. Yeah. 7.5. 1.75. Right. Oh, and same for this one. That's better. But I think we should go.
Oh, you are replotting it? You are replotting the whole thing?
Yeah, we just want to kind of zoom in on the object at the center here a bit more. Just because that's where the kind of action is going to happen. And we might want to go in even further. Yeah, we do. 0.25. Okay, I think we're good.
Okay.
So this should be relatively interesting when we get it all sorted. But it's difficult to think about. Oh, yes. This is 4-dimensional. And we I don't think we need 4 dimensions, actually, because we're projecting off a sphere. So we only need the coordinates for the cube.
Euclidean.
Yeah, exactly. So what are the coordinates for the cube? They're like, I suppose we can make them out of these because I'm too lazy to look them up. But, and again, yeah. I suppose we just delete the 4th dimension of each one. Or no, actually, we are using a computer, so we should speed this up.
Oh, yeah. It just removes the last item, right?
Exactly, yeah. Instead of doing it by hand. Cell 8 and underscore equals cell 8. I have to think about what I'm doing here.
The 4th coordinate. Remove the 4th coordinate.
Yeah, up to 0, 1, 2, 3, because we came from 0. So up to 3, I think. For I in cell 8. And we go. Yeah, that should do it. Okay, and then we want to turn that into a set probably, because there's probably, you can see there's duplicates. Oh, crap. Unhashable. It's a NumPy array. Oh, right. Weird. Cell 8 equals set. Some sets can be a bit annoying to work with. List set. Oh yeah, let's try that. And list I. Oh gosh. To list.
The syntax.
That's just the thing about
Is this Python? No, it's not Python.
I'm just going to delete that. Yeah, it is Python. Yeah. Delete that and then go. What the heck? Oh, unhashable type list. Can you not have a set of a list? Oh, you'd have to go.
Or list set.
Oh, yeah, that's right. So we're going to have to stringify all of these. Turn them all into strings. And then it works. And then we have to turn them back. So those should be the coordinates of the cube. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that looks right. And then we go. list I for I in cell 8. Oh, dang it.
Oh,
Yeah, this is where things get kind of annoying.
you have to get the right syntax, right? I mean,
um,
oh, you have to get a string, right? You have to get a string again.
well, what we can do is we can just cheat a bit here because what we wanted was just to get to a certain point, which is this point. So we'll just copy these and we'll just edit them straight as they are. Suppose I could have written like eval.
Yeah, it's small number of data, right? It's a small set of data. You can as well.
Yeah, I think I could have written eval string. Let's try that. Oh, I did write it over string, and then you could go.
Now, when we are doing this, I suddenly started remembering, and just we'll talk about later on the episode. But what I think about superluminar, it may be working like our computer program. Like you can say cell 8, right? And you can redefine and get a different value. Cell 8 equal to some other value, right? But it stores that value essentially, right? The same location. Unlike our algebra, in the algebra you cannot do that. But in algorithm, when you do the computer, you can do that, right? Superluminar thing may be working like that, in the sense that it could be infinite thing, but then you say that is equal to some local thing times that, still it will be equal to the same superluminar cogmate. So I'm thinking along that line. I think that will probably tell how everything is superluminar, but the local or observable universe comes out of that. It's interesting
Yeah,
thing.
I agree. It seems that's where my research seems to be going as well. So, and when I
You may
say
have
my
common
research,
point there.
the work we did last week in remember we were talking about superluminal speeds,
Yeah.
and that time you go into imaginary time and then backwards imaginary time and backwards normal time. So
The own thing.
Is it part? That's kind of separate to own, but it's not entirely separate. Like because we have the fundamental domains on the hypersphere, so it can connect that way. It can also, but it could be an entirely. It wouldn't even need to reference own. It could just sit by itself. And but it does seem like there's some potential results from it that, like you say, there seems to be like superluminal aspect to everything, even if it's not, doesn't even appear to be moving, which is weird. Also, there's something else going on though that, it seems to connect a bit to, not directly to your work in that it confirms it or anything, but it more sort of echoes some of even the early work that you did on the PDP circuit. Where you have this thing that which I always I thought was a very interesting idea and is almost right. So what you're trying to get at sounds really good, but there's just something missing in the components. But I really do like the idea of, what is it, like an electron?
If you have a large thing, right? So I would think initially there was no monopoles, nothing like that. It's just noise, right? The noise, essentially a noise, it's going random. At some point, at some local regions, you have some vortices forming. That can happen. I think you can prove mathematically also. Eventually, I want to talk with mathematicians. You can prove that if you are random numbers or infinite numbers, random is going random. At some point, at some locations, you can have a local cell or vortices you can create, because shear dynamics, from the shear dynamics. And that local cell will start to have character of PDP in a hot PDP cell. So that's the idea, the physics. I mean, that's a very large conjecture, but I'm saying that's the crux of the whole thing. Essentially, any dynamic system, because anything times infinity is still infinity, right? So in simple mathematics, so it means that if you have infinite system and it is going random all over the place, fluctuating, at some point it can create a local heterogeneity. So that's, if we call infinite homogeneity in a
Yeah.
sense, cotton, because a noise infinitely will be infinite homogeneity or homogeneity, whatever you can call it. But in that one, it can create a local inhomogeneity. The local inhomogeneity is sufficient. If it's stabilized, can form a cell, and that's sufficient to start like a nucleus for creating eventually a real universe. So it's also conforms to the condensate. So the whole thing is like infinite condensate. Out of that, you have evaporation of these local things, and then so you can form that. You can condense back to that. So but in that process, it forms the real observable universe. That's the whole the large picture of the whole thing.
Uh-huh.
So everything can be the way it is. So it doesn't have to have origin per se, the universe, like Big Bang or anything. But essentially, it was going on and still going on. But in that process, it creates this, things that eventually become consciousness and all those kind of things. I think that's one of the things you are talking about last, consciousness. I was talking about consciousness. You said that's something that can be stitched into this thing. And I was thinking a lot about that with time loop, all those. They all seem to make sense, but I had to put it because we had to prove these things.
Yeah.
So, but the conservation of time is a big thing. I think I got out of this, and that will be a big thing. We'll talk because I believe finally it has to be conservation laws. If we don't have conservation laws, we cannot derive anything. We cannot get any physics out of it. So the conservation. That's why people were always, they knew at that time, the time of Maxwell, even before that, they knew when they did that thermodynamics, they knew unless something is conserved, you can, anything go out of favor, right? Without conservation, how can you say how can you study any system or anything, So, but the momentum conservation is not possible. So nature is hinting something at that, and that hint is that things are not finite universe. Is not finite velocity, but it's superluminar. But out of that, you create all this stuff. So that is the main thing. So time conservation occurs in the observable universe, the real universe, because now we can prove the energy times time
Yeah.
is equal to a Planck, constant, in the quantum level. So that's conserved. We know that is true. If something is energy time, energy times time is conserved, and if you show that the time is conserved, then we have the whole conservation law we can create. So that is the whole crucial thing. So I think, instead of momentum conservation, it is the time conservation. And what that means, then you have umbrella model and all that. I'm thinking a lot about that and seem to be working out. I can even create like a UFO type thing with umbrella
Oh,
model. Yeah,
cool.
that's eventual exotic physics out of that. So like Sputnik, you can create like Sputnik effect. And I
Yeah.
may even do a project here if possible, because all with kids, all you need is something that is upside down umbrella, and you know and then umbrella proper, and and then you move around and it creates
Yeah.
a lift, and then you put them together, it become like like a balloon or Sputnik, and do we get a real lift and a gravity lift? That will
Yeah.
be a project. So very simple.
Cool.
May
No,
not.
it
Yeah.
sounds fun. It reminds me of I don't know. So, oh. You know what
Yeah,
I'm?
Emmanuel sent a recent one, right? I have not looked into it too deeply, but he sent a YouTube video of something. Somebody who was what was that? The
Not
recent
sure.
one. Thank you. Yeah, he sent a recent one. Oh, about the I think it's about the electrostatic. Somebody used electrostatics to
Uh,
to create a propellantless uh, a spacecraft without a spacecraft without propellant. That's it.
yeah.
Because electrostatics. So then I replied about the Van de Van de Graaff generator. So
Huh,
Van de Graaff generator. People are done even school experiments that you can create a conveyor belt, right?
yeah.
Electrostatic, and it can move things without any fuel. So it's an
Mm,
interesting thing, and it can be used even for road system. If you can create a road like a conveyor, we don't have to use fuel for our cars. The car can run without fuel on that. It's an interesting. You can test that. So that's all
mm,
future exotic things, technology. So there are a lot of applications. In real life, if somebody can
yeah.
develop, use that for engineering. But I think that's a cool idea.
Yeah.
And then,
Go ahead.
Emmanuel's talking about the warp, right? The superlunar warp thing. He presented in one of the things about the vacuum, how
Yeah.
the vacuum create its own propulsion. So that ah,
Yes, indeed. I'm sure. So just to go back to this for a second. You see, I'm trying to plot. Those are all the galaxies, and
uh-huh,
these are the coordinate values for the projected cube.
uh-huh.
And then we plot both of them on the same plot. But I'm not seeing. I only see. I'm only seeing. Oh, maybe it's because we're too zoomed in. That's it. There we
uh,
go. Uh, so based on this, Rajan, yeah,
uh-huh.
it looks like this out here is the outer sphere. This in here is the inner sphere. So all of these galaxies are
They're
on
in
the
the sphere.
they're on the inside, yeah.
Ah. So you're just magnifying. You're just amplifying the center, right? In a kind of like amplification.
No, no, I was doing
No,
that earlier
resolve.
when I had like, huh? When I was doing this, I could zoom into the center, but
Ah,
we weren't seeing the projected points of the cube which lie on the surface of the hypersphere.
oh, it's a
Now,
resolution. It's like
now,
resolving it.
yeah, this is to solve the problem that I was talking about with the hypersphere that we thought initially we were thinking that I suppose it's just here we were thinking that this was the boundary of the hypersphere, but
Hmm.
actually this is way out here.
Oh, it's
So
inverse, right? It's inverse transform, right? Is it the inverse transform?
what is inverse transform?
Because you take the thing and do inverse transform. So whatever is outside will go inside, and
Oh
whatever
no,
is inside.
that's different. Yeah, that's a different issue though. Yeah, yeah.
Ah, okay.
That's these yellow things in here were the inverse.
Where is the Earth, the Milky Way, Earth, and all? Where is it? Inside that?
Yeah, it's in the center, so it would be in the center of all of that, very
Oh,
center.
good.
So it's right there in the center of this. So just let me think though, because this is only the 2D version. We still have to construct the 3D version. And for that, we should probably go back to this happy fellow over here. Yeah, we should do that.
Is it still a Euclidean or is it four dimensional?
Well, technically, four-dimensional is still Euclidean, but yeah, you're right. It's four-dimensional. No, we just used 3 dimensions to create 2 dimensions. Now we need to create 4 dimensions.
To create 3 dimensions.
Yeah.
Go one up.
Yeah, you have to go one up to go get what we're looking for. But
Like
still,
right?
this is a result, you know? Basically, it means that if we were to just go on this, the only galaxies that are safe from destruction are these ones here in the middle.
Outer regions.
Everything in here is in danger.
The crunch. Is it a big crunch? Part of the big crunch type thing?
Yes. Everything out here will just transform in this area, so they'll be fine. Everything out here is fine. So everything out here is basically, we could consider on or inside the surface, because the surface is a volume. So that's good news. I mean, good results. So all of the galaxies out here then are going to be what is projected to infinity in some sense.
Away from the gravity effects. Gravity won't affect.
Well, this will probably, out here will probably be antimatter.
Anti-gravity.
Antimatter. And no, I believe not anti-gravity, but rather antimatter. So everything in here is a type of, is ordinary space with ordinary matter.
So they're crunched by the gravity. Gravity will crunch them.
No gravity involved.
No gravity.
Just the rotation of the hypersphere. It's all an apparent thing. It's not real.
You know? Do you have centrifugal or centripetal forces? No.
Irrelevant. Doesn't matter.
Rotation.
Once you're inside the sphere, once you're inside the projection and the simulation, you're going to feel like all of the objects moving will feel those forces in some sense, but they're all fictitious. They're not real.
But it's not constant. The force is not constant.
It's constant if the motion is constant, and that's it. So that's a good result. So we can add this to the, I wonder, what's your opinion, Rajan? I'm going to save that, and I will probably.
Oh, for the conference, we are going to mention to the conference.
Have to, because we've just updated the theory. So what's your thinking? Should I edit my proposal, or not proposal, by paper?
Can in presentation you can always do that. I mean, as long as the general thing is that you're already giving a general thing, but your details are in the presentation, so you can always add that.
Right, but our details are basically, they're just, it's changing what we initially thought. This is going to change everything, though, Rajan, because
that's fine. I think.
Yeah, what it's
just
going to do
is edited abstract. You can do either before or this. You can give edited. I think it should be fine.
That's no problem. I'm not too worried about it. I'm just wondering what way to go about it.
You should mention that though. But if you are presenting a paper, sometimes they ask that they can publish a paper based on the conference. At that time, but sometimes they don't. Sometimes they accept it. Sometimes they don't. The first time they accepted for me. The second time they didn't, because it was a bit too much.
The paper, Rajan. They already accepted the paper.
No. For presentation, I'm saying for proceeding, that separate paper. Separate paper. They have a conference paper. They produce a conference paper separately. Proceeding.
Well, if they do that, Rajan, if they produce
they say send it to.
Finish the point I'm trying to make. If they do say, let's say they say, "Oh, we need a new paper," then that's okay, because I can rewrite this paper. Subject. Anyway, just to go back to what we're talking about. So initially we had this as the surface boundary, which was 43.2 megaparsecs. Now we will have this volume here this volume here be the inner sphere. So that's way out there somewhere, even beyond the image there. It's way out here. So that could be, if this is 43, this is 86, 120, right? 160, 24. It's probably, I don't know, it's probably like 300 megaparsecs out, yeah, to this. And if that's 300, then this is going to be, this could be, I mean, obviously we're just eyeballing it here. We'll do the actual maths later on, but so that's, what is that? 2,700 parsecs, megaparsecs.
That's well within that, right? Observable.
Oh yeah. Oh yeah. Oh, this isn't that far out at all. The universe stretches for much, 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 much longer. Yeah. In fact, based on the own, you know, the stereographic universe model, it is infinite, obviously, on the tangent plane. But oh yeah, so the point I'm trying to make is, if this is the inner sphere, what did we say this was? Around 300 megaparsecs. So we can redo the math that we had here. So this volume here will be 300 megaparsecs, and this, oh, no. Yeah, so how do we calculate that? 1/3 of the outer cube distance. So if we said the outer cube distance was 2,700, did we? Megaparsecs divided by 3. So it's going to be, it's 900 megaparsecs, roughly. I mean, obviously we're talking roughly here. 900 megaparsecs for the radius of the hypersphere, which changes this value. And then, so this will be 1,800 megaparsecs. And then we'll have to calculate that. And then we'll have to calculate this and that. So this is typical, I think, and a good warning not to, you know, well, I've recalculated the size of the hypersphere numerous times. And each time I'm like, I have it correct, you know, I'm certain that this time it's right. So I am certain that this is right, though. How do you think? Do you think we're doing it correctly? I don't see how we could be.
Yeah, if we can write a story about it, I mean, you can create the proper physics story. I think it should be fine.
What do you mean create the proper physics story there?
In the sense that how does it link together, all of them, you know?
Oh yeah, so well, I mean, are you maybe because, you know, you have your kind of research and the stuff that you're thinking about a lot. With, you know, and then I'm thinking about my thing a lot. So you're then like trying, if you're trying to understand what I'm talking about, maybe it's a bit.
Yeah, you can get published. I think you know, the thing is that
you basically understand what I'm saying, don't you? I mean,
yeah. The basic concept, I get it. Yeah.
Okay.
Because even the other one, you know, they sent it to some journal. He didn't accept, but I myself sent to another journal. I got that published. So I don't think there should be any problem.
Oh, you're talking about something different now. What is this thing? There's something
the previous conference presentation. I think last year or before.
Oh
that.
yeah.
So did you? So like that, it can happen. Yeah.
So you sent that to them, and then they accepted, and then but they didn't publish it as a conference paper.
Journal. No, they have some journals. They sent it to, so that journal couldn't publish that because they say. But I sent to my own journal, some other journal, and they published it.
Well, that's fine, because if they were to say, hey, we like your paper, if they said, hey, we like your paper, we'd like you to publish it or something, just on the off chance.
They said that. Yeah, it's up to you.
My point. If they say that to me, I will just say thanks very much, but
Yeah.
I don't
They
think.
themselves
I
say
don't
that.
think.
Yeah.
I don't think. Can you wait a second? I don't think they will say that um, because based on the presentation, we'll be overturning everything in the papers. So I'd
Oh
have to
yeah.
write. I would have to write a
Yeah.
new paper, and then they would have to accept that.
Oh yeah.
And
Yeah.
so I don't know at that point what the protocol is, So, but it'd be
Yeah.
interesting. Okay,
Yeah.
so what should I name this then? Dimensions of hypersphere
Modification.
revised, yeah?
Yeah. Revisions.
Revisions. Oh. Or just revision because it's just one.
It's not
Dimensions of
modification, right? It's not modification.
It's not a well, it kind of is, but it's a severe
More like a
modification.
revision.
Yeah, we've
revised modification.
Well, we didn't revise the modification. We've revised the
Modified revisions.
Revised. Yeah, that's a good point, though. We've revised the SVM model. I think support vector machine model revision. Revised.
Or revised SVM model.
Yeah, dimensions of.
Yeah.
Dimensions. That seems good. Because I just need something that explains what it is, so I remember. I had to look it up later on. There, that was actually pretty good. We got what we wanted done, which is what we always do generally, right? We always get some results if within a reasonable time frame. So that was another success.
Oh yeah, today we did quite a lot of good work. I mean, the editing and
Sure.
But I checked that briefly, during the break, and then the one before October, there are a few we are not done, but we can see.
Oh yeah. Actually, you know what? It's fine because, like we said, we got the main ones done that were, that were real important, and I think all the other ones can be just general discussions. We don't need to revise any more titles.
Okay. Yeah, in general, it should be okay.
Yeah, it's totally fine. So awesome. So a lot more work to do now, and we need to revise all of the dimensions of the hypersphere. It's looking like the diameter of the hypersphere is around 900 megaparsecs. So, I mean, what does that even mean?
Yeah, you have to interpret that. Yeah, what it is.
It's huge. But that sounds right. It should be quite big, I think. 900, I mean, we'll see. I was all like, when we had 14.4, I was thinking, oh, that's a significant number. But now, thinking that maybe the number significance element side of things, kind of basically numerological.
900 megapascal is almost a billion. Almost a billion megapascal.
What is this? Is this the observable universe?
Yeah. Wow.
Yeah. But you have to remember, we're not dealing in terms of like observable universe.
Yeah, it's much beyond that.
Yeah. Because when we talk about a diameter of the hypersphere contains everything. So, and it's a diameter in the fourth dimension. So it's not a distance we can travel. We can't even travel a single.
Dark matter, maybe dark matter or dark energy there.
Oh yeah. Well, I mean, a gravitational well could take you far enough into the hypersphere. Like a black hole could take you maybe even close to the very center of the hypersphere. So that would be. Or I don't know. I mean, but that's certainly plausible, because the hypersphere would warp. And then,
whether our rule, whether it has meaning, the ruler of the based on the observable universe, but it may not be that may not apply to the other, imaginary things. It doesn't have any dimension per se,
What doesn't have a dimension? The hypersphere.
Imaginary.
What imaginary
thing?
There's no imaginary things involved here. We're dealing all in real numbers.
Yeah, infinite. If you are talking about infinite universe, I don't think it has We cannot put
No,
any
no, the
number to it.
hypersphere is the hypersphere is not infinite though. It is.
It's finite.
It's a finite. It's 9. We just discussed that. It is a diameter
900.
900. The tangent space is infinite, but that's only an apparent infinity anyway. So all good.
And
so we got that sorted now, and
of course, we are talking.
It's nice to get some good results, and
yeah,
we're moving along now. So next week we will continue with this, and I think that we'll probably solve, because we've already done the first one. It took me a long time because I was so tired, but we did get there. And next week we'll be able to do it much faster, and then we'll move on to we'll actually calculate all the dimensions then of the hypersphere as well. And then if we have time after that, we will move on back to what we were looking at, which is more of our joint work into the 24 cell time.
And the 6 universes, six type of 6 different universes.
Yes, exactly. We're going to see what the results of that will be. So there should be some really cool stuff coming out of that. And there's loads more stuff that we've got to cover as well in future ones. But then I think we'll take a bit of a break. We'll have your history of physics, and then we'll resume with the ongoing kind of relentless smashing of the mysteries of the universe. Okay, later.
Sounds good. Thank you. Have a nice week. We'll see you next week.